Hello. The purpose of our training today will be to familiarize the apprentice with the AC Power Center Simulator. This is part of the testing for the West Virginia State Certification exam, and we'd like to consolidate that training with making the apprentice familiar with troubleshooting in a linear fashion, line by line, as well as in a safe manner, that he can use these skills not only for certification but in his day-to-day life as a repairman. A large part of successful troubleshooting is being able to recognize the component and know what the actual component looks like in reference to the print. As you can see here, we have a print for this box, but the print looks nothing like the box. The symbols used on the print represent various components on the box. I'm going to point to a few of these and show them to you on the actual unit to bring you up to speed on what they look like. The first one would be the KT1. That's a transformer. That's a real popular symbol on many drawings. KT1 on the actual unit is this component here. Next you have GCS1. There's a contact GCS1. It's actually part of a larger system, and that contact is located inside this component here on a little ice cube relay. We have a 40 watt 500 ohm resistor on that print, and that 40 watt 500 ohm resistor is right here. The next thing on this line would be a UVR. The UVR, again, is part of a larger component. It's not visible, but its leg wires that connect it to the circuit are visible. And they're on a terminal block right here. The UVR itself is located inside the circuit breaker. It controls the breaker. We have two circuits that you'll be troubleshooting. One for circuit number 1 and one for circuit number 2. And circuit number 2, although they are individuals, they're powered from the same source, and they're identical with the exception of the ground monitoring used. The ground monitoring on circuit 1 is an impedance type ground monitor. The ground monitor in circuit number 2 is a tone type or audio ground monitor. The contacts, for all practical purposes, are the same. It's just the different device to close those contacts is the only difference. There's a third circuit here, the main circuit. The main breaker is located on the rear, and it has an emergency stop push button. It's also located here, just the same type that we use underground on the back of our power centers underground. And it also shows a door switch, which is a cat whisker type switch, a lid switch, just as the type that we use underground. And it's located here. This part of the circuit is testing circuit for the ground trip test to assure that the function of the ground fault circuit is intact. It's a test that's required by the government that you administer regularly. And the ground trip test switch is located on the back of this panel right here. And the small transformer that supplies the power to operate this circuit is right here. It's listed as KT3. There's an 8.2 ohm 11 watt resistor located directly adjacent to the transformer right there. And the rest of that circuit is wire. The main part of the panel, illustrated on the floor of the display, is not energized, and it's only used in one of the problems given by the state. And it is illustrated here. Again, these are popular common symbols on lots of prints. Main breaker, delta delta transformer, lightning arrestor, 3 banks of transformers, a main breaker on the rear of the box. You have a zigzag transformer that we use to derive a neutral for grounding purposes. It's located right here. You have a ground trip relay. It's located here. And the current transformer that feeds that ground trip relay right there. This symbol here is for the receptacle and plug for circuit 1 and circuit 2. And they're located on the front of the box. This is the plug for circuit number 2 and its corresponding receptacle. This is a plug for circuit number 1 and its corresponding receptacle. The monitored equipment for circuit number 1 and circuit number 2, we've replicated what's used by the state in making a plywood box with a circuit breaker and a grounding bus inside. And that is our monitored equipment. If this were actual mine equipment, circuit number 1 could be a pump, it could be a roof bolter, a battery charger, any number of things that will be supplied by this power circuit. It has an impedance monitor. Circuit number 2, with a audio or tone type monitor, could be expected to be a roof bolter or a miner or a shuttle car. Something that would routinely employ a tone type, or they often refer to as a wireless monitor for circuit number 2. These power system parts that would routinely be the higher voltage part of your power center are not used in the problems that the state has you test on. But in fact, we'll be going through them because the test is only the first step of our ultimate goal. We have to have you test and be certified, but we want you to be a good repairman as well. And unfortunately, all of our problems don't just lie in one area. You have problems could be occurring in any part of the box. There's a grounding resistor on this print, 18.5 ohms. That's this component here. And you'll routinely be examining ground resistors as part of your daily life. Okay, we've completed identifying the components and comparing them to the corresponding symbols on the print on the rear of the display. This is the front side. This is the part that you would routinely see in normal operation. You would have a module, a section for each circuit. This is circuit number 1. Each circuit is powered by the same supply, but they operate independently of each other. So we have a module for circuit number 1. Here we have its circuit breaker. There is a receptacle, a plug that plugs into the receptacle, the cable that runs from the power source here to the machine. We use these plywood boxes here, as we spoke of earlier, to symbolize a machine. It has a machine breaker and a grounding bus for the ground and monitor to be hooked up to inside the machine. This is the ground monitor unit. It's labeled on the print as GCS1, Ground Check System 1. This is the ground trip test switch. You would operate this switch to test the ground trip circuit. Over here we have circuit number 2. For the main part, they are alike. Circuit number 2 is a module powered by the same source, but it supplies a separate circuit, and it's operated independently of circuit number 1. It has a circuit breaker for circuit 2. Has a ground trip test switch that you would test the ground fault. This monitor, as you can see, is somewhat different. This is the wireless monitor that we spoke of earlier. Audio monitor, tone monitor. They all mean the same thing. The receptacle for circuit 2 and its plug. These wires that extend from the end of the plug here, these are part of the simulation. I can give you various problems by unhooking and connecting these wires, these jumpers. This is the cable going to the machine powered by circuit number 2. Here we have its breaker. You'll note some small control wires here that are the filter for the audio monitor, and a grounding bus for the ground wire and the common wire from the filter to connect to. This would be symbolic of a machine powered by circuit number 2 with an audio or a tone type monitor. Okay, fellas, as with anything that you would encounter underground, the safest possible way to troubleshoot any electrical circuit is with continuity tests with the power off. You can do some troubleshooting, no repair work with power on, but it's safer by far. Anything that can be troubleshot without power should be. That's best. So this box is powered by a 120 volt power supply, plugged into a normal wall outlet with this cord. This is the cord for the box. And prior to troubleshooting, we're going to make this cord safe by disconnecting, visible disconnect, and installing a danger tag and a lock. And after the cord is locked out, you take the key away, keep the key. The key with you. Even though we've locked it out and disconnected it from the source, we're going to take a moment to make sure that we have no power with a voltage detector. As you can see, the voltage is absent. There's no voltage found anywhere in the box. That's an important and necessary part. Okay, let's proceed to the actual solving of some of the problems that an apprentice may encounter at the state test. How the test is administered, they have a set of cards. Each card is called a problem card, has a different problem. And the problems are installed on the board by the operation of these toggle switches. You may note that the panel for the toggle switches and some of the terminal strips you'll see on the panel are not illustrated on the print. So what we have on the box that is not on the print, we ignore in our troubleshooting method. Now, the first problem that the apprentice may encounter, if you would draw this card, it's more or less a lottery. You just pull a card and read the card, and the fellow who administers the test at the Office of Miners Health, Safety, and Training, he will throw a switch and put you on the board. The first problem, problem card 51, it reads, none of the control circuit will operate. The primary of KT1 is not energized. That's a pretty big clue. The primary of KT1 is not energized. As before, when I showed you before, we said this is KT1 on the print. The primary is from the source, is not energized. Now, normally on a power center skid that you'd be working on underground, the primary would be the 480 volts, the same as the rest of the skid. The primary supply for the control would be 480. But the simulator runs on 120 volts for the classroom here. So it has a 120 volt primary source. It's a one-to-one transformer. There's no step down or step up. Now, by the primary not being energized, that would lead you to believe that somewhere between where the primary circuit originates at the input and the primary of the transformer, we have a cable fault or a problem in either a wire or a fuse. Note that these are toggle switches that we install the problems on. The toggle switch is either going to be made or open. Now, that limits how sophisticated the problem can actually be. But in real life, it could be a variety of things. On this particular panel, the problem is an open wire. Now, I'm going to show you how to find the open wire, but it would more than likely be a fuse blown in a real problem. So to start off with, we're going to use an instrument here to measure continuity. This is a fairly common brand. This is a triplet Model 60 multimeter. It can check AC volts, DC volts, as well as continuity checks. It has two probes, and what we're going to be measuring here is continuity. So I'm going to set this to read resistance times 1. The X1, X10, X100, X1K, X10K, those are actual multipliers. Keep in mind the ohm meter reads exactly in reverse to virtually every other analog instrument that you'll read in your life. On your speedometer, on your gas gauge, on most everything you read, the farther the needle swings to the right, the more you have. On an ohm meter, 0 is on the right. You're measuring resistance, how much resistance you have. The more resistance you have, the poorer the circuit is. Okay, the more opposition to the flow of current. A needle that stays on the left indicates an open circuit or an infinite amount of cable resistance. I should zero this instrument first. To get an accurate reading, you have to adjust the instrument until it actually reads 0 when the leads are shunted together. I'm going to attach one probe to the number 1 wire where it originates on the print. That would be here. And just as if I were following a map, I'm going to go to the other end of the wire, which is on a fuse. FU1. This fuse is located here. Wire number 1 is marked with a marker. On this type of dash mount fuse, usually the line side, or the side toward the source, is attached to a rear terminal. The terminal on the side is usually the load side, but the wires are marked and are also color coded, so that won't be an issue finding our way. With one lead attached to one end of wire number 1, I'm going to put the probe to the other end, and as you can see the needle movement, it reads 0 ohms resistance. That's as it should be. This wire is indeed intact. Now, I'm going to read through the fuse to the other probe, right there, and again, it reads no resistance, which is as it should be. I first read to the line side of the fuse, and then I moved to the load side of the fuse. That's as it should be. The fuse is intact. I have no resistance to the flow of current through the fuse. Now, I'm going to proceed through the circuit and read to the other end of the wire attached to the load side of the fuse. This is wire number 3. As you can see, it goes to H1 on KT1. Wire number 3 is an orange wire. It has a wire marker of 3. I go to the other end of it on KT1, wire number 3, and I have continuity. Okay. That is as it should read. Now we're going to install the problem by operating this toggle switch, 51, and do the same checks again. with the problem installed. Now, again, you always zero your instrument to start to give you the most accurate reading possible. And I'm going to attach my two probes together. The instrument is 0. The first point that I can check wire 1 to, load side of the fuse. Wire 1 is intact, as the needle indicates by going all the way to 0. There's no resistance. Go through the fuse to wire number 3, the other side of the fuse, the load side of the fuse. As you see on the drawing, that's this point right here. The only thing I've added to the circuit is the fuse. I'm reading through the fuse. And the other end of wire 3 is on KT1. And it indicates an open circuit. The needle didn't move at all. No movement. The circuit is open. Note that I've left this and I've followed this line from point to point, just as if you're taking a map and go from destination to destination. These wires, although there are a multitude of wires on the print and a multitude of wires here, all of the wires aren't bad. And each wire you can check with a simple continuity check from one end of the wire to the other with the instrument. And each wire has 2 ends. One probe on one wire, one probe on the other. If you have a circuit, that wire is good. Just as you were going to follow a map to a certain destination, you would go from landmark to landmark. You start at one point, follow from landmark to landmark. That's the same way that you troubleshoot in a linear fashion. I'm going to put the switch back, take the problem off, and the wire is good. As a more realistic problem that an apprentice may encounter underground, I'm going to disconnect the fuse, and for troubleshooting purposes, this would be the same as if the fuse were blown. Wire number 1 reads intact, coming from the source. From here to wire number 1 at the fuse is good. Now I'm going to read through the fuse, as we did earlier. As you can see, it reads open. That would indicate the fuse is open. That's a more often encountered problem than having a wire open. The second problem card number 52. If you should draw this problem, it would read, none of the control circuit will operate. The primary of the control transformer KT1 is energized, but there is no voltage on the control circuit. Again, as we referred to earlier, KT1 on our drawing is here. The primary, stated in the problem card, is energized, so the problem won't lie in that way. But it says none of the control circuit is energized. There's a lot of information to be gained from the written card. It says the primary is energized, but none of the control circuit. The last place we know we have power is at the primary. So we'll begin with continuity test on the secondary of KT1 and follow those circuits out. Secondary of KT1, X4 and X1 are the terminals involved, to a terminal board, and then to the fuse. This particular type of diagram is known as a ladder diagram. You can see by the drawing it's got upright and rungs. They're common to all the circuits, but each individual rung is a separate circuit. This circuit here is for circuit number 1. This rung is for circuit number 2. This rung is for KT3. They're all from a common supply and have a common return. I will refer to the left-hand side of the drawing as the line side. customarily the controls are on the line side of the circuit. And I'll refer to the right-hand side of the drawing as the return side. The return would be after the circuit is complete, the conversion is complete, the work is performed by the electricity, and it returns to the source. So we're going to begin our troubleshooting at the secondary of KT1, terminal X4, the first point that we can access. I'm going to place my instrument up on top here where everyone can see it. Make sure it's stable. Always, before you begin any test, you check your instrument. Zero adjustment. And the secondary of the transformer begins with a terminal X4, wire 7. And that can be found right here. Okay, I'm going to attach one lead. And the first point on the drawing that it shows wire 7 going to is here, to a terminal board. And as you notice, the meter sweeping all the way to the right indicates no resistance. That wire is intact. From wire number 7 going to the terminal board, it then goes to the fuse for the secondary fuse, labeled as FU1. It's a 5 amp fuse. Again, the line side of this type fuse mount is usually directly in the rear. And here we have, again, no problem there. The circuit is intact. And we're going to read through the fuse to wire number 9. And 9 is again intact, or the fuse is intact. It's not blown, it's not open. On the drawing, what we've checked so far, we attach one probe here, read to the terminal board. From the terminal board, we read to the line side of the fuse. Then we read through the fuse, always checking back to here. So we're at wire number 9, and everything appears to be intact. The next point that you can access wire number 9 is on GCS1, terminal 1 of GCS1. Wire number 9 is a white wire, and it's labeled as wire 9, and it's easy to find right here. You can put your meter to it. You'll see a small amount of cable resistance. All conductors have some resistance. That's a small amount. And where you attach your probes can also cause just a tiny amount. And that doesn't indicate an open. Okay, that is how the circuit should read. That is a proper circuit for the secondary of the control circuit. Now we're going to install the problem. The second switch, 52. And beginning as I did before, the secondary of KT1, X4 terminal, wire 7. First place it goes is to the terminal board listed on the print. There we have it. It's a good circuit, no resistance. The next point, as is indicated, from the terminal board is to the line side of FU1, wire 7. And there you have it, a good circuit, no resistance. The next point would be through the fuse to the load side of FU1. This checks the fuse as well as the fuse holder, and it's good, no resistance there. The next point that we can access would be terminal 1 of GCS1. This is GCS1, ground check system number 1, the next rung of the ladder. And we read to there. Whoa, we have an open circuit. Wire number 9 is broken between the load side of FU1 and the terminal 1 of GCS1. As you can see, there's two possible places for it to be broken. Well, let's try to pinpoint that a bit. What I'm going to do is read further into the circuit to the next point shown. GCS 2, terminal 5 has a 9 wire. It's supplied by 9 as well. I'm going to read from 1 to 5. Remove the probe that I have on terminal 7, and using it, read wire number 9 to wire number 9. And we have a good circuit. So that proves that wire 9 is intact from here to here. Our problem must lie here. To further prove this, I'm going to reattach my probe to terminal 7. Put this probe on wire 9 on GCS 1 and operate the switch. As you can see, the needle sweeps forward when I operate the switch, indicates a good circuit. There you have it. The next problem card. Problem card number 54. Circuit number 1 breaker cannot be set because the UV will not pick up. Proper control voltage is present at the secondary of KT1. GCS number 1 contact is closed. All of the control voltage is dropped across the 40 watt 500 ohm resistor. There's no ground fault on the power conductors of circuit number 1. Circuit number 1. As you can see, there's the 40 watt 500 ohm resistor referred to in the problem card is in series with UVR for the circuit breaker number 1. Its purpose for being there is to accommodate the GTR tips closing. The contacts for GTR make when you have a ground fault, the ground trip relay tips, when they close, if it were not for this resistor in the circuit, that would make a short circuit. There'd be no load between wire number 8 and wire number 9 that supply this. It'd be a direct short. And the result of that would be a blown fuse. Anytime that the ground trip relay contacts closed, whether you had a fault or you had pressed the test button, anytime these contacts closed, it would make a short circuit. This resistor is there to provide a load to limit the current to avoid blowing this fuse. Well, there's only two problems that could cause all the voltage to be dropped across that resistor and that condition to be sustained. Both of them involve the closing of these tips. Now we close them intentionally when you depress the ground trip test switch for circuit number 1 to check the function of this relay. You intentionally close those tips, and by closing the tips you provide a bypass for the UVR, and in essence you starve that UVR. The current will flow the path of least resistance, and rather than flow through the UVR and be converted to magnetism, it will take a direct path across these contact tips, and this UVR will lose its magnetism and cause the breaker to trip. When you intentionally press the test circuit, it closes these tips, and that will cause all the voltage, all the current to be dropped right here. But we don't have the test intentionally depressed. So one of two things: it can either be stuck, shorted, or these tips can be shorted, stuck. They're normally open. If they fail, and they fail in a closed status there, it's just as if you had the button depressed. So what we're going to do is troubleshoot the circuit and try to determine which one of these two problems we have. The problem illustrated that we don't have a ground fault on the power conductors for circuit number 1, so that won't be an issue. Here we go. First thing that we're going to do is set our meter up where we can see it good. Turn the meter to the R times 1. Zero the instrument. And it always takes a tiny adjustment. Okay. Now our instrument is zeroed. I'm going to take a moment here to determine for certain that the power is off. And it is. There's no power on any of the incoming circuits. So, of the two components listed that may be GTR, which is located right here, its tips should read normally open. Now, I haven't installed a problem yet, so this should be a normal reading. And as you can see, they read open. No continuity. And the other position is the GTT switch, which is right here. I'm going to attach one probe. These are very small connectors here. A little bit difficult to get a probe to attach to, but you can do it. Read that. Now note that reading. It's not completely open, although the print shows this is a normally open switch, but the circuit doesn't read open. The reason that you read that, it's approximately 9 ohms read, is if you would follow this circuit back, you'll see that it has a path, a parallel path. And an ohm meter is not unidirectional. You can't direct what part of the circuit. You can't more or less aim your ohm meter. When you attach it to point, it's going to read any path it can take. And in this circuit, if you look at the drawing, you'll have a parallel path. Now, the value of this resistor is listed as 8.2 ohms, and you have the wire involved as well, and you have this little transformer, KT3, and that accommodates or accounts for the 9 ohms that is shown by the meter. We're reading an open switch with 9 ohms. Now, should the switch be closed, that reading will change. Just push the GTT switch and watch the reading of the meter. 0 ohms. When you closed it, your meter was reading directly from here to here. Now, those are normal readings. Let's open this panel, install the problem number 54. Make the same tests. The only components that could make these symptoms that we just saw are the ground trip relay contacts. Their reading's unchanged, they still read open. And this GTT. Now you recall, when the switch was depressed, it read 0 ohms resistance. In its normal status, it read 9 ohms. And there you have it. It reads a dead short, 0 ohms resistance. So our problem, the normally open ground trip test switch for circuit number 1 is shorted. Okay guys, so this is problem number 55. The main breaker cannot be set. There's no mechanical problem with the breaker. Control voltage is present on the secondary of KT1. ESPB contacts are properly closed. There's nothing wrong with the UV coil. Again, the problem they give you, although it tells you one thing that can't happen, but it tells you a lot of things that are happening. It narrows the field a bit for you. It says there's no problem with the breaker, no mechanical problem. It says you have control voltage on the secondary KT1. That's a good place to begin troubleshooting. It says the ESPB contacts are properly closed. There's nothing wrong with the UV coil. The ESPB contacts, they're here. It says the UV coil, there's nothing wrong with it. It says you have control voltage on the secondary, but this breaker won't close. In order for this breaker to close, we need to have a circuit through this line here to the UVR and then back. None of the problems in the simulation are going to be found on the common or the return side of the circuit. And that won't necessarily be true in your real life problems. They could lie anywhere. But for the purpose of the exercise here, none of the problems will lie on the return side. All of your problems are going to be on the line side or the power side. Some people refer to it as the hot side, although they're both sides are energized. The problem states, no problem with the UVR. The main breaker has no mechanical problem. ESPB is properly closed. You have power here. Well, looking at the problem, or looking at the print, the problem can only lie in wire, or maybe the door switch, because everything else is mentioned as being in good shape. So the last point it says you have power is the secondary of KT1. That'd be a good place to begin. So we're locked and tagged. We have a visible disconnect, lock and tag. I'm going to, just as a precaution here, take a voltage reading, make sure that we have no power, and none is indicated. I'm going to take our meter, set it up here in a comfortable spot. You can see it good. And as a beginning, we're going to start at the place where they said we had power. So I'm going to put the black probe, I'm going to attach it with the alligator clip to wire number 7. Begin there. Now, the first point I can check from there is the terminal block for wire 7, right here. That's shown on the print, right there. The next point, the line side of FU1, wire 7, and it's good. The next point, the load side of FU1. At that point right there, wire number 7 changes numbers. It becomes 9. As you can see, 9 is common to all of the line side of this circuit, just as 8 is common to every rung of the return side of the circuit. Wire number 9 now. The next point that we can pick up on the machine to check for continuity would be terminal 1 of GCS1. As you can see by the meter, wire number 9 is intact. We have continuity to there. That's this point here. Now the next step that we can take, terminal 5 of GCS2. And that would be here, terminal 5, GCS2. As you can see by the meter, we have continuity to there. So this circuit is intact from the probe we have attached here, through the terminal block, through the fuse. We've touched down here, we've touched down here. The next place to check to is the door switch. Wire number 9 on the door switch. This is the door switch. And we're going to put our probe through and go to 9 here. As you can see, it's good. Now, the door is open and the switch should be open. I'm going to read across the switch while we're here, show you the operation of the switch. As you can see, it's open. Now, when I close the door, it would close the switch. Note the meter reading. The meter closes, or shows a closed circuit, shows continuity through the switch. Got a little resistance there though, not much. All right. That is as the circuit should read. Now let's install the problem. We'll come over here and open the door. I'm going to operate the toggle switch for problem 55. And there we go. Now the problem's installed on the board. Making the same checks we just made. Start off at wire number 7 on the secondary of the transformer. Read to the terminal board. And we have continuity. From there to the line side of the fuse holder, we have continuity. Through the fuse to the load side of the fuse, FU1, we have continuity. There the wire number changes to 9. From 9 on the fuse holder, the first point we can reach is 9 on GCS1, wire 9 on terminal 1. And from there we go to wire 9 on GCS2. We still show continuity. And we're going to go to the door switch. It's the next point in the line. Wire 9 on the door switch. That's an open circuit. There's no continuity. So our problem lies between this point here, GCS2, and wire number 9 on the door switch. Now to further pinpoint this, to see, I'm going to read from GCS2 to KT3, the H1 terminal of KT3 for wire number 9. And we'll move my black probe and we'll use it on the terminal for KT3 and take my red probe to 9. I've got some continuity there. I have a circuit. That tells me the wire 9 is intact from GCS2 to KT3. It's only open here. That pinpoints the problem. And that's that. Problem card number 56. Should the apprentice draw this card for a state test, it will say breaker for circuit number 1 cannot be set because the UV will not pick up. The UV is okay. GTR is in its normal de-energized state. GCS1 will not pick up. The GCS1 contacts will not close. Okay. The problem gives you quite a bit of information there. Now, here, up until now, we've been talking about mostly problems that are associated with the circuitry on the control. But this is somewhat of a different problem. It says that GCS1 will not pick up. As we mentioned earlier, GCS1 is the contacts that control the circuit breaker from the ground continuity monitor. Now, the ground continuity monitor contacts won't pick up. You have to have a certain situation has to be met before the ground continuity monitor contacts will pick up. You have to have a continuous path on the ground conductor in the receptacle to the machine and then back. It has to have a loop. This wire here goes to the ground conductor. This one here is the pilot or monitor wire. And that has to be a continuous path. It's shown here on the circuit number 1 receptacle and plug. The pilot wire going to the equipment frame. The ground wire going through the plug to the equipment frame. This portion here on the drawing is the cable. that connects the machine to the power unit. Our machine is that box that we discussed earlier there. It's symbolic of a machine. It has a main breaker in it and a grounding bus. And that will be the frame of the equipment. Now, before this monitor can be satisfied and close these contacts, it must have a loop from the pilot pin in the cat head to the equipment frame and back, or vice versa. It has to be a circuit. All of these impedance monitors work on basically the same principle. They'll put a small reference power or reference voltage on the ground and pilot to the machine and back, and if that circuit is met, then it'll close a relay. Pull a relay in and close a set of tips. This is the coil that has to close, and these are the tips that have to make. These tips are the same as these tips. Same thing, just drawn in a different spot on the map here. When these tips close, it enables power to flow from the line side of the transformer or the power side through the circuit to the UVR. When the UVR is energized, the pickup that they refer to is a literal pickup. It becomes a magnet. There's a coil that, when energized, becomes a magnet, actually lifts a linkage off of a trip mechanism in the breaker and allows that breaker to set. And it has to have a return back to the source. Now, the problem states that GCS1 won't pick up, won't close. The problem is probably not in the system, not in the power center. The problem is probably in the machine. And that's what we're going to check now. This is what you would see both at the testing center or in a workplace. When you first approach the power center, you see you have a monitor light in a tripped light showing. Well, normal operation would be to press the reset switch, and it did reset. I don't know if the audio can pick it up, but we could hear a relay close. That GCS1 contacts are now made, and then you could latch and set the breaker. Okay, this is the power circuit plug, the cat head as it's called, the cable going to the machine. And should this be a real power center, this machine would now be energized. Okay, that's what we want to have. But on our problem, that's not happening. Okay, I'm going to put my gloves on. Although the power portion of this box is not energized, I'm going to put my gloves on, and to simulate this problem, I'm going to open the ground monitor conductor at the machine. Now, as you can see, the red tripped light is now on. I'm going to operate the reset. To no avail, it doesn't work. So we have a problem. The monitor won't reset. You don't automatically assume that there's a problem with the ground monitor unit itself or with the power center itself. We're going to check the machine first. And to do that, I have to uncouple the cable coupler. I'm going to light right here where it'll be convenient to test. Take the instrument. Before we do any testing, we're going to lock and tag. Now, this is de-energized. It's unplugged. We're still going to make a voltage test. This is not the only cable on this section. There's no voltage. Now it's safe to handle. Take the meter, zero the instrument. I'm going to read continuity from the ground conductor to the monitor on the end of our coupler. Now, some people have trouble telling which one is which. If you remember from your studies in the book, the ground continuity monitor conductor is broken first when the cable is uncoupled or the cable coupler is removed. As you can see, this one in the center here is much shorter than the other two. As the cat head is hinged up and levered up, it would be the first one to break. So we know that's the pilot or monitor blade. According to your studies as well, the ground blade is the last one broken. These blades are cut at an angle with a long edge and a short edge on top here. As this thing is levered out, the long edge will stay in contact after this one is broken. The ground is supposed to be broken last. That's my ground blade. And we have an open circuit. This should read continuity, but it does not. I'm going to connect this monitor wire back up to show you what it should read. From the monitor pin to the ground blade, it should read a full circuit, full scale continuity with low resistance. There you have it. Should the grounding conductor begin to fail and its resistance changes as it fails, as it becomes less competent, it will give you a different reading, ohmic value. If that reading should increase 3 ohms, the monitor should detect that and open the circuit breaker. This test button here is to check that. If the monitor is properly calibrated, when you depress the test switch, it trips and you have a red light. You can reset it. If the breaker is set, you depress the test switch, the breaker falls. And it's important to keep this thing calibrated as closely as possible as that point, so that as you lose your grounding circuit, you're aware of it. Problem card number 57. The breaker for circuit number 1 cannot be set because the UV will not pick up. The GTR is in its normal de-energized state. GCS1 picks up, however the contact GCS1 appears open. On this problem, we have circuit number 1, the machine's plugged into it. We reset our monitor. It resets. We attempt to energize circuit number 1 by closing circuit number 1 breaker. It won't go in. It stays in a tripped position. Well, we have a ground monitor circuit. We can apply the test switch and it trips, reset, sets back up. Try to set it, and it won't set. So we obviously have a problem with the circuitry inside the power center. We'll have to go to the other side to check this. Well, we discussed earlier the importance of doing all possible troubleshooting with power off, making continuity tests. But this particular circuit, to properly troubleshoot it, it involves the closing of a relay, and that requires the power to be on. So we're going to have to change our methods just a little bit. Instead of making continuity tests here, we're going to take some voltage readings. You can work on energized equipment in a limited fashion, troubleshooting only, by wearing low and medium voltage gloves. And the only tools you can really hold in those gloves is your test instruments. And that's what we're going to do now. Now, all right, our problem, if you could see it on the print, we have control power. We have the monitor appears to be closing, but the breaker won't set. The UVR is not becoming energized. It's not allowing this breaker to be closed. The UVR is more or less a trigger. When it's energized, it makes a magnet, lifts a linkage up off of a trip mechanism in the breaker. And that's not happening. It's not closing. Contacts are closed, no power here. So what we're going to do is we're going to read for our power. I'm going to start here at this terminal board contact, or 0.7, and read through my circuit and see why, or see where I lose my power. See why I don't have power all the way. To do that, we're going to don low and medium voltage gloves. I'm going to take our instrument and note that we're on the continuity test. We've been reading ohms on ×1 scale. I'm going to change that to read AC voltage. And I'm going to choose a scale higher than what I anticipate finding in voltage. And I've done that. We anticipate having a 120 volt control circuit. I've chosen a 300 volt scale. And it will be indicated on this line here, below the dark thick line, the next scale under. Now, I'm going to don my low and medium voltage gloves. I'm going to attach my black probe to that same terminal 7. We've began there many times today. And I'm on terminal 7. I'll take my other probe and read my control voltage at the transformer. That reads, as you can see, between 110 and 120 volts AC. Now, with that 120 volts from 7 to 8, I'm going to read from 0.7 to the fuse. If this wire is open, I'll read 120. If it's closed, read 0. And I read 0. I'm going to read through the fuse to wire 9. It reads 0. Keep in mind, a voltmeter reads differences in electrical pressure. It reads, if both probes are on the same potential, then it will indicate a difference of 0. And that's what we have here, a difference of 0. From wire number 9, on the load side of the fuse, the next point I find it is terminal 1 on GCS 1. Again, I read 0. There's a 0 difference. For all practical purposes, electrically, this point here and this point here at the source are the same. The next point I will read is terminal 10. There we have it. Wire number 10 on terminal 3, I read 120 volts right here. If this contact were closed, then there would be no difference and it would read the same. But in fact, it's open. To further pinpoint that, I'll take a probe and read from 9 to 10. I read 120 volts. That indicates an open circuit where one terminal on terminal 1, wire 9 is reading to this side of the transformer. One probe on terminal 3 is reading to the other side of the transformer, and then open contact between 120 volts. I would say you had a bad relay. Problem card number 58. If the apprentice should draw problem card 58, it reads, monitor for circuit number 2 will not drop out when the TRS number 12, that's the common lead to the machine filter, is disconnected. The troubleshooting that we've done on the prior circuits involved an impedance type monitor. The impedance monitor, you have a reference voltage between the ground pin and the pilot pin, and that circuit is extended all the way to the machine. As long as that loop is intact, the monitor is satisfied and it will close a relay. That's GCS 1 contact between 3 and 1, and allow power to be put to the UV. On circuit number 2, you still have the relay. It's GCS number 2. It still has to be closed to put power to the UV. Those circuits are identical in that respect. What is different between the two circuits is what closes the contacts, the GCS contacts. Now, circuit number 2 employs a wireless monitor. The wire that you're less is the pilot wire. There's still wires involved, but you don't have a pilot wire dedicated only to the monitoring of the ground wire. The audio or tone or wireless monitor, they're called by all 3 names, employs a completely different system. It puts a high frequency signal, approximately 4,000 hertz, on the phase wires. There's a filter internal to the monitor. A transmitter puts the signal to the filter. The filter then puts the signal to the phase wires, and it's carried to the machine on the phases. Phase 1, phase 2, and phase 3, the power wires. On the machine there's another filter. It's identical to the first, and as its name implies, it filters any other noise off of the signal, like the 60 hertz power that we run. It filters that away, and it returns that signal cleaned up to the TRS common. On this particular unit is a white wire. Frequently it's a green wire, the common wire from the filter. You can see that wire right here. That's this white wire that's standing up right here. Now, when the white wire leaves the filter, it's attached to the frame of the machine, and you know the frame ground wire is attached to the frame. So that signal is put on the ground wire, sent back up the cable to the coupler, through the receptacle, and when it passes through the receptacle on the conductor, there's a CT. It picks that signal up, or it recognizes that signal. And when that signal returns, the CT closes GCS2. And GCS2 functions much the same way as GCS1 does. It allows the control power to go from wire number 9 through the remainder of the circuit to energize the UV for circuit number 2. Now, the problem reads when the TRS-12, the common wire from the filter, is broken, the breaker doesn't fall. That is the same as saying if the ground wire is broken, the breaker doesn't fall. And that's the whole intent of the ground monitor, to open the breaker if you lose your ground. So if it won't drop when you break it at the filter, it won't drop if the ground is broken. In order for this machine to operate correctly, for this system to work correctly, the ground blade inside the cable coupler must be isolated electrically from the shell of the cathead. The shell of the cable coupler can't be connected to the ground blade. The signal must go from the filter, through the ground conductor, through the cathead, through the receptacle, and then be picked off by the CT on the inside to satisfy the monitor. If the signal should by chance come in contact with the shell of the cathead, of the cable coupler, then the monitor's defeated. It's bypassed, it's tricked. Now, what we're going to do is I'm going to break that TRS number 12 conductor and see if my breaker falls. In essence, I'm disconnecting the ground from the machine. First, let's reset the monitor. It's ready to go. We'll reset the breaker. I'm going to put some low and medium voltage gloves on. What should happen is the breaker should fall if this system's working correctly. As you can see, when I separated the filter from the circuit, nothing happened. It didn't work. That is a problem. Now, to determine if this cable coupler shell is grounded, the cathead as we call it, is grounded, I'm going to have to open it up here and make a meter reading. Check and see if we have continuity. I'm going to open the breaker. Uncouple this cathead. And make a reading. Now, although we've uncoupled this thing from the power source, this cable is laying in close proximity to other cables that are probably still energized on the section. Okay, although this circuit is disconnected from the power center at this point, the cable lies in close proximity to other cables that may indeed be energized on the section. So we won't assume that the power is off just because this one's disconnected. I'm going to make a voltage reading, make sure that these conductors are not energized, and they read clear. And then with my meter set for a continuity check, and we'll zero the meter. And with the meter zeroed, I'm going to check for ground continuity between the ground blade and the shell of the cathead. And for proper operation, we can't have any. Now with all these pins, it's still fairly easy to tell, even, you know, for the novice, which one is the ground conductor. You'll note this one, due to the angle of the blade, is long on top. When the coupler is levered out of the receptacle, this one would be the last one to break, the last one to come away. And by law, the ground conductor and the cable coupler has to be the last. Here we go. Look out. We have a full scale deflection, no resistance. The ground blade is in contact with the shell of the coupler. Okay. Now, for the purpose of our training, I've made a connection at the rear of the cable coupler. This connection here will interrupt. I can use that to show you a proper reading. With the black lead attached to the ground blade, it should read an open circuit to the shell. As you can see, it does. An open circuit. Okay. Problem card number 59. Control voltage is present. The circuit number 1 breaker can be set properly. The breaker will not trip when the GTT push button is depressed momentarily. The breaker will not trip when the GTT push button is depressed momentarily. Well then, according to the written statement, you have control voltage. GCS1 is made up. The monitor circuit is satisfied. We have power to and through the UVR. We have a circuit. The UVR is picked up. It's allowed the breaker number 1, to latch and set. But our test circuit isn't operating. When we depress the test switch, ground trip test switch for circuit number 1, what should happen is a current should flow on this circuit through the switch on a wire that passes through the ground trip CT and then back to the transformer. It should make that loop. When it does that, the CT detects current flowing on wire 17, and it in turn induces a current in the CT that powers the GTR relay. This GTR relay, that's the ground trip relay. That's the relay that should respond, close these contacts to trip the breaker in the event of a ground fault. Ground fault meaning a phase conductor has came in contact with the equipment frame or the ground wire in the cable and is then grounded. You have phase power on the ground. The ground trip relay, when that current is detected by the CT, the ground trip relay coil should become energized, should close these contacts and bypass the UVR. It should shunt power around the UVR, causing it to fall out. When the UVR falls, it in turn trips this breaker. This breaker staying closed is dependent upon this UVR being energized. When the GTR contacts close, it gives the circuit a path of least resistance around the UVR, robbing it of its power. It drops out, trips this breaker. Now that circuit, the ground fault circuit, is so important that you know that we're required to test it. And one way of testing that circuit is to depress this ground trip test switch. It doesn't actually put a ground fault on the circuit. It doesn't make contact with a phase to the frame, but it simulates that. This wire, there's a small voltage applied, 8 volts AC, and it's passing through an 8.2 ohm resistor, and when you depress this switch, it energizes this wire, 17. 17 passes through the CT 7 times. It's looped 7 times, and by looping it 7 times, you multiply its current 7 times, and then it returns to the control transformer. The resistor is here for the same purpose this resistor is. If it were not for that resistor, when you close the switch, it would be a short circuit, and it would damage either the wiring or the transformer, KT3. When a problem states, when you depress this, it doesn't work. So let's make a couple of checks here and see why it doesn't work. After you understand how the circuit works, you know that in order for the GTR to trip this breaker by robbing the power from the UVR, it has to be connected in a circuit with wire. So that's what we're going to check first. We're going to make sure that the GTR, the ground trip relay, is indeed connected to the circuit. And to do that, we're going to make some continuity tests over here. I'm going to take the meter, set it in its perch. You always zero the meter before you begin. Every time you change scales, and frequently thereafter. You should zero your meter to make sure your instrument's reading correctly. Gives you good information. I'm going to make sure that our circuit is disconnected, locked and tagged. This is the power supply cord. As you can see, we have a lock and a tag on it. Now I'm going to take the key with me. I'll take a voltage test before I begin my troubleshooting to be sure that I have no power on any of the incoming lines. And I do not. There's no power. Now, the part of the circuit that we're concerned with is this GTR. So let's read it and its wires associated with it first. Okay, I'm going to read the circuit that connects it to the UVR circuit on 11C. And we have a terminal block here for the UV. The UV is actually part of the circuit breaker. It's internal to the breaker, and it's not readily accessible for reading, but its leg wires are. I'm going to put one probe on 11A, and I'm going to read to 11C on top. And there you have it. I have a circuit. That's as it should be. Now the other probe, or the other side of that circuit, is wire number 8. As I said earlier, for the state examination, there are no problems involving the return wire, wire number 8. And in fact, you may encounter those in real life. Now we're going to install the problem on the power center now. I'm going to open the test panel and close switch 59, put problem 59 on the board. Now, by doing that, we've changed the wiring. Now, I'm going to begin by reading the wire 11 from the ground trip relay, the contacts of the ground trip relay, to terminal 11 on the UV terminal block. It reads open. As you can see, let's check our meter. You frequently check your meter as you're troubleshooting. It still reads open. Well, let me read the other side of it just to make sure. Wire number 8, and it reads intact. Wire 11 reads open. Let's check our print here. This 11 from the UVR terminal block to the GTR contacts reads open. That being the case, if the GTR contacts should close, then they would have no effect on the UVR because the current cannot be redirected and the UVR would not be interfered with. It wouldn't lose power, so that wouldn't operate. GTR contacts close without 11C wire intact, no effect. That's the problem. Problem card number 60. Circuit number 1 breaker cannot be set because the UV will not pick up. Proper control voltage is present at the secondary of KT1. GCS number 1 contact is closed. The UV coil is not open. Circuit number 1 breaker can't be set. These problem cards really give you a lot of information. If you're discerning and pay close attention, circuit number 1 breaker can't be set. This is the circuit that controls circuit number 1 breaker. It says the UV won't pick up, so we know the UVR doesn't have power. It says that proper control voltage is present. We have control voltage here. The secondary is producing 120 volts. And it's present. GCS1 contact is closed. It says the monitor is satisfied. That contact is closed. So that's stating it's connected all the way through there. And it says the UV coil is not open. So it says the UV coil is not open. UV won't pick up. Proper control voltage present. GCS1 contact closed. UV coil is not open. With the information given, I believe we'd be well to start at where we know we have power, we have proper control voltage. Let's just clip on. X4 at terminal number 7. That's what we'll do. I'm going to take our instrument, put it up here out of the way. Let's zero it. Calibration of the instrument is important. Sometimes problems are not always on or off. Sometimes they're just in degrees of difference, just in a few ohms difference. If your instrument's not zeroed, you won't detect that. Just takes a moment to do. I'm clipped on 7. Problem states that we had proper control voltage on the secondary. I have continuity to the terminal board, wire 7. I'm checking to the back of FU1, the line side. I have continuity there. I'm going to check through FU1. The fuse is good. The fuse is not open or blown. At this point, it changes number to wire number 9. The next point that we can read wire number 9 from the fuse is GCS1, contact 1. Here's wire number 9. And indeed it's good. A problem stated that GCS1 was closed. The contacts for GCS1 that close, wires 9 and 10 go to terminals 1 and 3 on the unit. We've completed a continuity test up to here. So now I'm going to move my black probe and attach it to this terminal 3 for wire 10 and continue to follow the circuit out. So here we go. Let's move this black probe to terminal 10, or wire 10 on terminal 3, I should say. And the next point that can be read is on the end of the 40 watt 500 ohm resistor. On this particular unit, that's the wire in the back. And it's good. We have continuity. Now, here's where we're going to use some of our meter reading skills. You can see on this top scale, they have a 0 all the way over here on the right and an infinity symbol all the way over on the left. Well, these analog meters, they're not usually a linear device, in that the same movement of the needle, the same distance of needle travel, doesn't always have the same value, ohmic value, at different points on the scale. From 0 to 1, about a ½ inch of needle movement just for 1 ohm. From infinity, complete open circuit, to 500 ohms is about a ¼ inch. Between 500 ohms and 100 ohms is about a ½ inch. So we need to choose a scale, a multiplier, that will be easy to read. That'll put us somewhere in the middle of the meter, an easy place to read on the instrument. By the print stating it's a 500 ohm resistor, I'm going to choose something that would be easy to read. 500. I'm thinking times 100. Times 100. So whatever this needle indicates, times 100 will be my reading. I'll change scales and we'll recalibrate the instrument. Oh, it's not really off much to that scale. Okay. I'm going to attach one probe to one side of the 500 ohm resistor and read the other side. As you can see, reads just almost 5, just almost exactly 5. 5 times 100, 500 ohms. So that tells us that we've checked from GCS1 to the line side of this resistor, and the wire is good, has good continuity. And then we've checked the resistor itself, and it's reading in the approved range and approved value for this device, 500 ohms. I'm going to leave my black lead attached on the load side of that and continue to follow this to the UVR. Reading wire number 11. The next point it goes to is to the UVR terminal block down on the bottom here. And it reads good. Okay. Wire number 11 also should read to the GTR contacts, and it does. Okay. There you have it. That's how the circuit should properly read. Now, we can open the door here and throw one of the toggle switches there to put a problem on the board, see how it reads with a problem. This is problem number 60. Okay, starting from the beginning, we're going to attach on the source, wire 7, X4 terminal at KT1, take it to the terminal board, wire 7, and we have a circuit. I should pause here a moment and reset my meter for just a continuity test on these wires to ×1 circuit. And go to the terminal strip. Here we go. we're good. Go to the line side of the control fuse, FU1, wire 7. That's good. Read through the fuse to check the continuity of the fuse. That's good. Fuse is not open. If the fuse were blown, when you read that circuit, it would read this. I'll take the fuse out so you can see. Just read an open. That's a bad fuse. We don't have a bad fuse though. We've got a good one. And it goes to wire number 9. From there, we're going to be following wire number 9 to terminal number 1 of GCS 1, wire number 9, and we have continuity. And with those, with the power off and those relay tips open, we can't read any farther without moving our meter. So I'm going to move my black probe to wire 10. That's on the terminal number 3 on the load side of the GCS1 contact right there. Wire number 10 goes to the 40 watt 500 ohm resistor, and it's intact. You can see by the needle we have a full scale, no resistance. But we have to read this 40 watt 500 ohm resistor. Now by our previous check, you know that this is a good resistor. Note how little the needle movement is though. That would appear to be, you know, not much of a circuit at all. But the needle's not, or the meter's not adjusted properly to read the component of that value. I'm going to change my scale to the 500 or to the 100 scale. It stayed zeroed. I'm going to put the probe on one side and read this resistor. And as you can see, it reads very nearly exactly 5. 5 times 100, 5 on the dial times 100, 500 ohms. So the resistor is good. We're going to proceed on wire number 11 from the load side of that resistor. From here, we're going to go to this terminal here, which is a little terminal block that powers the UVR and the GTR. And the first place I'm going to check is wire 11 on the UVR. It reads open. Wow. Let's check it to 11 on the GTR. Still reads open. We're reading an open circuit between here and this point and this point. Just to further pinpoint that a bit, let's read from the UVR to the GTR, and that will tell us if it's that wire. And we have a circuit there. Let me change my meter back to times 1. And we have a circuit with virtually no resistance. Okay. By making that check, we verified that we're intact from here to here, but open from here to here. That's that. Problem number 61. This problem is new to our group. All of the state offices don't have exactly the same problems or exactly the same machines. And here in the very recent past, we encountered a new problem. It's new to us. I'm sure it existed for a long time. Problem 61A, let's call it. This problem is to be solved without power being applied to the skid. All troubleshooting should be done with an ohm meter. The problem is as follows. All three-phase outputs indicate a single-phase condition. Single phase. By saying single phase, that indicates a loss of a phase. The three-phase outputs mentioned are, circuit 1, the power circuit going to machine 1, and circuit 2, the power circuit going to machine 2. Okay, it says all the three-phase outputs are single-phased, indicating a loss of a phase. Well, looking at our drawing, we can deduce quickly that they're both supplied by the same source. They're supplied by the delta-delta transformer. And the delta-delta transformer is supplied by the main breaker. This little block here that says isolated, you won't find that on a power center underground. That will be particular to this training model machine. This is to keep you from inadvertently energizing the power portion of this circuit. And by isolated, that basically means disconnected. This wires 1 and 2, they are not isolated. They're connected to the 120 volt input to power up the control circuit. The power circuit, on the other hand, is isolated. Well, we're going to check for our single phase. We're going to start at the source where it says isolated and read from that main breaker to the delta-delta transformers. That would be the high voltage input on a normal power center, on a real power center underground. The high voltage input to the transformers from the main breaker. To do that, we're going to take our instrument, zero it, and we have a 0, properly calibrated. Okay, I'm going to attach the black alligator clip to the first phase. Looking on the drawing, that would be right here, bottom of the main breaker. We'll read to the first transformer, and we have no power, or no continuity, I should say. Going to the second transformer, again we have continuity, and to the third transformer we have continuity. Okay, we want to say that phase is intact. Now I'm going to the second phase, which is in the middle. It's this phase here, off the bottom of the main breaker. Read to the first transformer, and we have continuity. The second one, we have continuity, and the third one, we have continuity. I believe can believe that phase is intact. Now the last phase would be this one. We have continuity, we have continuity, and we have continuity. Now that illustrates proper reading. That's how the circuit should read. Now I'm going to install the problem by flipping a toggle switch in our test panel and make the same checks again, find our problem. Problem number 61. I'm going to attach my black lead to the first lead, first phase, right here. I'm going to read to the delta-delta transformer. And we have continuity. To the second one, we have continuity. And to the third one, we have continuity. Move our test lead to the middle phase. That's right here. I'm attached here. I'm reading to here, to these 3 points. to the first phase. I have it. To the second one. I have it. And to the third one. And I have it. All right, we have one more phase. It's this phase here, from here to here. Uh-oh. No continuity. No continuity. Again, no continuity. This phase is open. Due to the nature of the connection of these three transformers, you know, H1 and H2 are on the first transformer, jumper to H1, or H1 is jumper to H2, H1 is jumper to H2, H1 is jumper to H2. If this circuit or this wire is intact, I should be able to read from this phase to any of these points with only slight variances in resistance. But as this is, I can read to none of them. So that indicates an open conductor from the bottom of the main breaker to the transformer. That's it. Problems 61 and 62 both read identical, and as follows. Audio monitor in circuit number 2 will not pick up. Proper power is applied to the monitor. As we discussed earlier, if you reset the monitor, it won't reset. You can set the breaker. Now, this problem and 61 and 62 have identical symptoms, and they differ only slightly. They both involve the filter at the machine. On one, the TRS-12 common lead is open. It won't allow the monitor to pick up. On two, one of the phase leads from the monitor filter is open, and it won't allow the monitor to pick up. By pick up, I'm saying when I reset, it will, put power to the UV and allow circuit breaker number 2 to be closed. Let me show you proper operation of it. With all of the wires intact, when I reset, the breaker trip light goes out, the closed light is on. I can set the breaker. For a test, push the test button, and it opens the breaker. Breaker trip. Reset, set the breaker. Now, again, if this TRS-12 common wire is open, with the TRS-12, the common lead open, we have our power on light. The system ground light reads open. The breaker is tripped, and it will not reset. I can press the reset button, and the monitor will not reset, and the breaker will not set. When I reconnect in TRS-12, the common lead to the filter was reconnected. Power light is on. System ground is closed. Push the reset button, it resets. The breaker will set. The other problem, 62, uses a phase. The monitor has 3 wires on the phase, the filter. When you open the phase, it says the system ground is open. It has a power light. It won't reset. The breaker is tripped, won't reset. And the breaker won't set. When we reconnect the phase, we have the power light on, system ground closed, the reset button turns the breaker trip light off, and the breaker will close. And that's all. Problem card number 63. If the apprentice at the test center should draw this problem, be circuit number 1 breaker cannot be set because the UV will not pick up. Proper control voltage is present at the secondary of KT1. GCS number 1 contact is closed. All of the control voltage is dropped across the 40 watt 500 ohm resistor. There's no ground fault on the power conductors of circuit number 1. Does that sound familiar? It should, because it's word for word the same problem as problem number 54 that we talked about earlier. It's exactly the same thing. At that time, I told you that the reason this 40 watt 500 ohm resistor is in place is so that when we close the GTR contacts to rob the UVR of control power for a ground fault trip, that would make a short circuit. It would connect X4 of KT1 straight through to wire number 8 back to X1 with no load. That would be a short circuit. And should you have a short circuit, every time the GTR closed, it would blow a fuse. It would blow a fuse, and you would not only lose this circuit, you'd lose everything powered by KT1. All of these circuits would become dead. So, strictly for the purpose of providing a load for this circuit, when GTR closes, we have a 40 watt 500 ohm resistor. We have one for circuit 1 and one for circuit 2 as well. Now, when we close GTR, instead of it being a short, the current being very high due to a short circuit, we have a load. And this load limits the amount of current that flows and preserves this fuse. Now, the only time that all of the control voltage is dropped on the 40 watt 500 ohm resistor is when the GTR is closed. The GTR, ground trip relay. Ground trip relay. You can see a couple of places where the ground trip relay is illustrated on the drawing. Right here on the ground trip test circuit, if you press the test switch making this circuit, it simulates a ground fault and operates the relay just as if you had a ground fault to test its operation, to make sure that it is indeed working. The ground trip relay here, this is the CT. This is one symbol for the CT on the power circuit. Same CT, different symbol on the control circuit. Okay, the power conductors are routed through the CT. Current transformer responds to a magnetic field, a flux that surrounds an energized conductor. Now, to induce, you have to have 3 elements. You have to have a magnetic field, a coil, and the CT is a coil. You have to have relative motion. Now, these wires are obviously not going to move, but we have 60 cycle power. And in 60 cycle power, if you should view a sine wave of 60 cycle power, you have the current flows upward. It's changing constantly in magnitude, and it peaks and then it goes down to a neutral, and then to a corresponding point, an equal point below neutral, and then back up. That's one cycle. And it does this 60 times a second. That provides the motion. As the current flows up, peaks down to neutral and then below neutral to a negative peak and then back to neutral. As the current flows in such a fashion, the magnetic field surrounding that conductor expands and contracts in the same manner. And that provides motion. The field is moving. These phase wires that pass through the window of the CT are not directly connected. You can see those here on the CT. They're not connected electrically, they're not joined mechanically. They're considered to be magnetically coupled. And as the field expands and contracts, it can induce a current transformer that will operate this relay. It will make electricity in a sufficient quantity to power this coil. Now, with 3 phases involved, they're offset 120 electrical degrees. And so while one phase is ascending, there's always a corresponding phase that is descending, so the magnetic flux stays at a comparatively constant level. There's no movement. While one of them is building, another one is falling, and the net result is a small change or a no change in the field. Should one of them become grounded, that changes the flux. That will either provide a gap or a constant that's not matched by another phase. And the flux field that's left is enough to induce and drive the relay. Well, we simulate that by pressing this button, and that puts a current on a phase that's unanswered by another phase. It passes through this coil 7 times, so it's multiplied by 7, and it will provide sufficient current to drive the relay just as if you had a ground fault. That's the only 2 conditions that will cause power to be dropped on this resistor, all of the control power dropped, and be maintained in that state. Is either this switch is shorted, stuck in a closed position, or these relay contacts that are normally open and should only close when you have a ground fault are shorted and stuck in a closed position. Starving the UV, putting the power around it, robbing it, and all the voltage has to be dropped here. So we have 2 points to check. We can check this switch, and we can check this GTR relay contacts. Let's go over to the skid here and do that. Okay, I'm going to take my meter, set it up in place here, preparing to troubleshoot this. And we're going to lock and tag. We already have a visible disconnect. This is a power cord for this skid. Place it in the lock box. Put an electrical lock on it and a danger do not operate tag. And put the key in our pocket. Now let's zero this instrument. And zero should be synonymous with calibrate the instrument. You're going to get an accurate reading by a properly calibrated instrument. Now, as we discussed on the print, there are only 2 points that can cause this particular symptom. All of our power being dropped on a 40-watt 500 ohm resistor. The only way that can do that is if the GTR, the normally open GTR contact, is closed. Now, a ground fault on the system would close that GTR, but you'd have to have the breaker energized, and it would close it only for an instant, and then it would be open again. The ground trip test switch could have failed in a shorted position, keeping it in a test mode, causing it to be closed all the time, or the actual relay itself could have failed and be closed, be shorted closed. So we're going to test this ground trip test switch and the GTR. This switch is drawn as normally open, and indeed it is normally open, but an ohm meter is a bidirectional device. You can't direct it to just read this switch unless you would isolate the switch from the circuit. So when we attach a probe from one side to the other, we're not only going to read the switch, but we're going to read the remainder of the circuit as well. And the circuit has an 8.2 ohm resistor that's used for the same thing this one is, to stop it from being a short circuit when you close it, and a small transformer, a 16 VA KT3. It's a 120 volt to 8 volt transformer, step down transformer to drive the circuit. So I should read approximately 9 ohms resistance if this switch is good. Let's see if it's good. I'm going to attach my black meter lead to one side of the switch with the alligator clip, and with the other lead I read, and as you can see, I'm reading approximately 9 ohms, which is as it should be. Now, the GTR should read open on its contacts, and I'm going to read from wire 11 to wire 8 on the 2 contacts on the GTR, and it reads open. That is as it should be. Now, with the problem installed, we're going to find one of those 2 readings to be changed. I'm going to open the door here, and using toggle switch number 63, put a problem on the board. Now, make the same checks over. I'm going to attach my black meter lead to one side of the GTT switch. There's very close quarters in there. It's not an easy connection to make. And with the other probe, I'm going to check the other side of the switch. I'm still getting an appropriate reading. Everything's good. All right, that clears the GTT switch. Leaves only one. I'm going to put one lead on wire 11 on the GTR and the other lead on wire 8 on the GTR. And as you saw, the needle reads a full-scale continuity. The switch, the relay, contacts are shorted, and that's our problem. Well, that completes the showing of the problems. Fellas, a few points I'd like to illustrate to you, not just for the purpose of certification, but in all the troubleshooting that you'll do. Listen to the problem, actually hear. Look at the problem and actually see. And use all the clues. And although there's a lot of wire and a lot of circuits, usually it's only one that's giving you the problem. Check as much with continuity as possible. Limit the checks that you do with power on. You're much safer with continuity. Lock and tag. You only have the one life. lock and tag. Test it before you touch it. Make sure you're safe at all times. When you're troubleshooting, use the print just like a road map. Have little destinations. Check from point to point, line to line. Each wire has two ends. Move from one end to the other for continuity. Read the print. If you can read the print and you can read your meter, there's nothing, there's no problem that you can't find. Doesn't matter. Whether it be a power center simulator, a power center underground, any other electrical circuits you choose to check. There's nothing you can't find. And that's all I have.